Welcome to this Concept Explainer, brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. Today, we are starting a deep dive into the introduction of Unit 10, Wave Optics. Our mission is to explain this topic so simply, so clearly, and so safely for your exams that you will lose any fear and remember the core ideas for life. So before we even open the book, I have a select question for you. Suppose you have two identical 100-watt light bulbs side by side and they're illuminating a wall. In the area where the light from both bulbs overlaps, how bright will that wall be?
Oh, that is easy now. If they are identical bulbs, the light should just add up. It should just look twice as bright everywhere, like 200 watts of light on that overlapping spot.
Logically, yes. That's what our everyday experience tells us. And in geometric optics, for the last unit, we only deal with rays. So intensities, they simply add. But here is where light gets really, really interesting. Wave optics shows us the truth. Two identical 100-watt bulbs do not create 200 watts of brightness everywhere. In fact, and this is the amazing part, if we use a special type of light, two sources can actually combine to produce a spot of darkness.
Wait, what? Light plus light equals darkness. How is that even possible?
I know, right? This counterintuitive behavior is the core mystery that wave optics solves. It shows that how the light is organized, that matters just as much as how much light there is. Okay, let's unpack this a bit. Our core idea is simple. Light is a wave, just like sound or ripples on water.
Yeah.
Geometric optics, from Unit 9, it treated light as straight line rays. And that works great for mirrors and lenses, no problem there. But it fails. It fails when light encounters tiny obstacles. Wave optics exists to explain these failures. Phenomena like diffraction, that's light bending, and interference, which is light canceling, and polarization.
Okay, so it's all about what happens on a very, very small scale.
Precisely. To understand it, think of light waves like traffic on a multi-lane highway. That's our highway traffic model. Now imagine two separate highways merging into one. If the cars on both are perfectly synchronized, we call this coherent, they arrive in these organized bunches.
So like a big wave of traffic.
Exactly. That's constructive interference, bright spots. And they also create organized gaps. That's destructive interference, dark spots. But if the cars arrive randomly, which is what happens with normal headlights, we call that incoherent, then it's just a uniform flow of chaos everywhere.
Just general brightness, no pattern.
Exactly. In light, that synchronization, that coherence, is the key to creating those visible organized patterns, those bright and dark stripes. And why do we need this concept? Well, geometric optics couldn't explain the colorful patterns you see on soap bubbles.
Or on oil films on water.
Yes. Or even how anti-reflective coatings on eyeglasses work. They work by canceling light. So wave optics enables all that. Lasers, fiber optics, holograms. They all depend on understanding light as a wave, not just a ray. Now let's build a mental picture. Imagine perfect parallel lines of wave crests. A plane wave marching toward a screen. And in that screen, there's one narrow gap. What happens?
It goes through the gap.
It does, but how?
Yeah.
That gap becomes a new source, radiating waves outward in a circular pattern. It spreads out. It's a diffraction. Now add a second gap nearby.
Ah, okay. So now you have two of those spreading circular patterns, and they will overlap.
They will overlap, and they create alternating stripes of constructive and destructive overlap, and that is the interference pattern we see.
I think I get the ripple analogy in the highway model, but one thing is still bugging me. If light is always a wave, why do shadows look so sharp in everyday life? Why isn't this wave bending obvious everywhere?
That is a very, very insightful question. We'll get to it in our misconception section, but the short answer is about wavelength. The wavelength of visible light is extremely small. We're talking around 500 nanometers. So for an everyday object, the angle of bending it's almost imperceptible. You can think of wave optics as just geometric optics viewed under extremely high zoom. We only see the wave effects when we look very, very carefully. And that brings us to our formal starting point. We have the concept. Now let's see how the insert book defines the fundamental unit here. The wavefront. Could you read the definition of a wavefront from section 10.2 for us?
Sure. It says, such a locus of points which oscillate in phase is called a wavefront. Thus, a wavefront is defined as a surface of constant phase. The speed with which the wavefront moves outwards from the source is called the speed of the wave. The energy of the wave travels in a direction perpendicular to the wavefront.
Excellent. Now let's re-explain that introduction by breaking down the 5 key elements of light's wave nature that we're going to study. First, the wave nature. We just have to accept the light as a wave because only waves can show diffraction, interference, and polarization.
Okay, that's the foundation.
Second, the wave parameters. Like any wave, light has amplitude, which is related to intensity, wavelength, frequency, and phase. And phase is crucial, so the key that determines what happens when two waves overlap. Third, coherence. We have to distinguish between coherent sources with a constant phase difference and incoherent sources with a random one.
And the interference patterns only show up for the coherent case.
Right. Fourth is diffraction. Because light is a wave, it must bend and spread when it hits an obstacle or a slit. And fifth, the transverse nature. We study polarization, and that proves light is not a simple wave like sound. It's a transverse electromagnetic wave. The oscillation is perpendicular to the direction of travel. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com. Okay, now let's use this core idea of coherence mathematically just for a moment. Suppose we have two waves, E1 and E2, of equal amplitude. Let's call it E0. If they're incoherent, like two normal bulbs, the intensities just add up. If the intensity of one is I0, the total intensity is just I1 plus I2, which is 2I0, a uniform brightness. Simple.
Okay, that's our everyday experience.
But if they're coherent, like from a laser, the resultant intensity is given by a formula. It's 4I0 times cos squared of delta by 2, where delta is the phase difference. Now, if delta is 0, they're in phase.
And the cos squared of 0 is 1.
So the intensity is 4I0. The brightness is actually doubled compared to the incoherent case. It's 4 times a single bulb.
And if they are completely out of phase, delta is pi.
Then cos squared of pi by 2 is 0, so the minimum intensity is 0.
The light is completely canceled.
Exactly. So this shows that two identical coherent waves can produce intensities from 0 all the way to 4 times a single wave's intensity. It proves why coherence, that organization, is so important. And really, this whole unit is the crucial sequel to ray optics. Ray optics told us what happens, Snell's law, for instance. But wave optics, using Huygens' principle, will now show us the mechanism. It'll show us why Snell's law must be true. All right, let's talk about 3 silent killers. Some misconceptions that can weaken your understanding and might cost marks in the exam. First, wrong idea. If two bright light sources are placed near each other, the region of overlap is the brightest possible spot.
Well, students think that because it's just normal addition from our daily experience, right?
It is. But the correct idea is that this is only true if the sources are incoherent. If they are coherent, they create interference patterns. That means you get points of 0 intensity, dark fringes, right alongside the brightest spots.
So coherence means you get a pattern, not just more brightness.
Perfect. Remember this hook. Coherence is the difference between brightness and interference patterns. Same light, different organization, completely different outcome. Okay, second wrong idea. Light always travels in straight lines. Shadows are always sharp.
Again, this comes from geometric optics, and it just looks true in daily life.
I know it does. But the correct idea is that light is always a wave, and it always diffracts or bends around obstacles. Always. But the angular spread is approximately lambda by d wavelength over object size. Since wavelength is tiny and the object size is usually huge in comparison, that bending angle is too small for us to notice, so the shadows appear sharp.
So diffraction is always happening, we just don't see it because the wavelength is so incredibly tiny.
That's the perfect way to remember it. Diffraction always happens. Wavelength is so tiny we never see it unless we look really carefully. All right, third wrong idea. Unpolarized light has no preferred direction of vibration.
That makes sense. The word unpolarized suggests randomness, or maybe an absence of direction.
That's the trap. The correct idea is that unpolarized light is actually a chaotic, rapid, random oscillation in all directions perpendicular to its travel. Polarized light is the simple one. It's organized. It oscillates in only one specific direction.
So unpolarized light is actually vibrating much more chaotically than polarized light, which is organized only, say, vertically or horizontally.
Precisely. Unpolarized equals chaos in all directions. Polarized equals organized in one direction. And a polarizer is just a gate that only lets through oscillations in its one direction. Okay, now let's create some memory anchors. To remember the 4 core phenomena of wave optics, just remember the word WHIP. W is for wave, H is for Huygens, I is for interference, and P is for polarization.
WHIP. That's easy to remember.
And the best phrase to remember the essence of this unit is simply, light is a wave, it bends, interferes, and has direction. Now, for a physical gesture, we can visualize polarization. Imagine you're holding a rope and shaking it randomly in all directions, up, down, side to side. That's your unpolarized light. Now, pass that rope through a narrow vertical fence slit.
Oh, okay. So only the up and down shaking would make it through.
Exactly. Only the vertical component of the shake can pass. The wave that comes out the other side is now vertically polarized. That simple mechanical filter. It demonstrates polarization filtering perfectly. So to summarize everything, here are 3 exam-safe factual points about the introduction to wave optics. First, light exhibits wave properties: diffraction, interference, and polarization. These are phenomena that geometric optics just cannot explain. Second, coherence is the essential prerequisite for observable interference and diffraction. Incoherent light, like from normal bulbs, only produces uniform brightness by adding intensities. And third, light is a transverse electromagnetic wave. This is proven by polarization, and it means the electric field oscillates perpendicular to the propagation direction. To get maximum marks in 12 CBSE physics, chemistry, and maths, visit profsam.com.
That is ProfSam, right?
Yes, profsam.com. Thank you for joining us on this deep dive into wave optics. Study hard and all the best.